Swayam Prabha. Digital India. Educated India.
Welcome everybody. We are going to talk about a very important topic, cyclohexanes. Cyclohexanes are a very huge part of your life, believe it or not. I know you're thinking, where am I seeing this six-membered ring like in a beehive? Well, turns out 2/3 of your food is made out of six-membered rings. Okay, that's all of the starch. It's made out of glucose units, and those are six-membered rings. Turns out most of your house is made out of six-membered rings, believe it or not. In North America, we build houses mainly with wood. Wood is made of cellulose. Cellulose also has glucose units linked differently. That's also six-membered rings. And if you're out in the summer, you're probably wearing cotton clothes, and that's also made out of six-membered rings, because cotton again is cellulose, which is a six-membered ring glucose unit polymer. So I cannot overemphasize the importance of six-membered rings when you're living in it, you're eating it, and you're wearing it. Okay, so that's how important six-membered rings are, not just for the bees, but for us as well, for the birds as well. Okay, so let's look at this. Six-membered ring, how is it? So if you're thinking six-membered ring like this, a flat ring, that is the most uncomfortable or high energy position for a six-membered ring, a flat ring. Okay, this is about 20 kcals high. So a flat ring like this is really bad for everyone, mainly because the angle is going to be 120. So that's deviating a lot from 109. 109 is what we would prefer. All of these hydrogens would be up and down, and you would have a lot of torsion here. Okay, so torsion is going to be high. So angle strain, that is when your angle deviates from the hybridization angle, that's called the angle strain. And I will write that down. Angle strain, when the angle between two bonds on an atom, not between other atoms, just on the same atom, deviates from the optimal hybridization angle. That is, sp3 would be 109.5, sp2 120, etc. Then what happens is, those bonds, so let's say you're squeezing these bonds, these are nothing but electron density here, so they're going to be repelling, and because of the repulsion, you're going to have a high energy. So let's say you're squeezing these bonds here, these bonds are going to come closer to each other, those electron clouds are going to be pushing, then your energy is going to get higher. Okay, then the energy increases due to repulsion, and that extra energy is called angle strain. So this is not good. Then what is good? Well, the reason why it's not good is because you have torsion also, and we already talked about what torsion is. The reason why it's not good is because of all of the torsion and angle strain, and I'll just draw these out just to make it pretty obvious that you have a lot of angle strain. I mean, if you look at it, if it's flat, you can see they're all eclipsed. Okay, now to relieve the eclipse, it can do many things. One of the things that it can do is, well, remove the torsion by pushing these up. Well, you can see right here between these two carbons, there are no parallel bonds. Therefore, the torsion's relieved. However, the rest of the molecule has got torsion because they still have parallel bonds. So this is a half chair. So we will take one of these carbons and just go up. So from here, it can go to a half chair. So all of these are going to be the same, but one of them goes up. So therefore, some torsion is relieved, but not all. You will have torsion between these parallel bonds over here. There's torsion here. Just here is going to be relieved, and here too you have 120, but here it might be relieved to like 109 when it goes up. Okay, so therefore some torsion and angle strain. This one's more than 20 kilocals. This one is about 10.8. Okay, so I would say more than 20 kilocals per mole. This is about 10.8 kcals per mole. All right, let's keep going. What else can we do? Well, if you relieve this and go up, why not relieve this and go up? That would be good too, because then you'll get double the amount of stability. Well, it's really not a perfect word out here as well, because if you look at this, you're butting heads here on the top. These hydrogens, these are called flagpole interactions, because you can see they look like flagpoles. So this flagpole interaction is increasing the energy. If you look at these hydrogens, and these two hydrogens are parallel, these are parallel, that means this electron density here and here are pushing apart, that's called and here too, these are pushing apart, and so it wants to rotate away from each other. Okay, so this is not really ideal, but it's certainly better than this and this, because you have less torsion here. So then this goes over to a boat, all right? So you can see these two are going up. So you have a boat, and the boat has got hydrogens that can be bumping into each other. That's called the flagpole interaction. And then you will have some torsion here, because these are parallel. And same here. So you'll have torsion here as well between these and these and these. So you'll have torsion. You may have removed quite a bit of the angle strain, but you still have torsion, and you will have flagpole interaction. Now, is that the best we can do? Well, we can do what you call a twist boat, like kind of twisted like a pretzel. Twist boats are also pretty good. Okay, so twist boat here has got about, this is 7.0 kcals. So it's coming down. And then let's look at our twist boat here. Our twist boat is just when you have, let's say, this and this kind of twisted up like that. That also relieves some of the flagpole to some extent, and some of the torsion also, just because they're not exactly parallel to each other. All right. So this one has a 5.5 kcals, I believe. So these also have some torsion, relief of torsion. So this has less torsion than here, and the flagpole is also relieved for this molecule. This is 5.5 kcals per mole. Okay, again, this is your twist boat. This is your boat. This is your half chair. And this is your flat. Those are all the different conformations that you could go through. Well, let's see, once you got it all twisted up, what else can we do? Well, we can actually, when you can see the torsion's less, the angle's less, we can go all the way down. There you go. This is the best position possible, and of all of the rings, this one is the best. You can't have a ring better than 6. Okay, 7, again it goes up, all right, and we saw that. So 6-membered rings are the best. You eat them, you live in them, you wear them. That's because they're the most stable, and nature has selected it over many, many millions of years. Why is it best? Because every time, just look at over here, okay, when I keep rotating, and see if you can see any bonds that are parallel. Look at this, that's completely away from each other, 60-degree angle. Okay, no torsion. Over here, no torsion. All right, so let's look at how we can draw this 6-membered ring. You can see there are 2 parallel lines here in the middle, and there's like a bird beak coming down, and then a tail going up. Okay, so let's draw those out. So start with the two parallel lines. Just draw them staggered like that. Then what you can do is you can think that you're reflecting this on this side. So think there is a imaginary mirror here, and you're reflecting this like that. And the same thing here, you're reflecting this line on here. All right, and then you can connect them. That's 4 carbons right there. Then you connect these carbons. It should be the same length and about the same angle, and you'll get a nice cyclohexane ring. Okay, that's this. Well, what about if you flip it? Well, when you flip it, you do pretty much the same thing. These are now going the other direction. They were down, now they're going to go up. So to draw the second one, take these 2 lines and put them up, facing up like that. Now you can do the same thing you did before, reflect this, so you are going to have a bond that's coming over here. And reflect this, so you're going to have a bond that's coming over here. Then you can take these and join them to get your other chair. So there's your nice 6-membered ring. All right. Then what about the other pokey sticks here? Well, you can see the vertical axial bonds are on alternate carbons. So you can see 1, 3, 5. Same at the bottom. So on the carbons, the alternate carbons 2, 4, and 6, they're vertically down. Okay. So we can draw these vertical lines. When you have a peak going up, the vertical line goes up. So this peak is going up, and the vertical line is going up. This peak is going up here, vertical line goes up. When I say peak, I meant like a mountain peak like that. You put your bond up. Here's another mountain peak going up, vertical bond up. All right. Then when you have a valley here, and then it goes down. A valley here, it goes vertically down. A valley here goes vertically down. So these are your 3 valleys. And they kind of come to this bottom point, and it's almost like you do a tube well down there. Those are your axial bonds. So those are your axial bonds. Those are the easy ones to draw. How do you draw the equatorial bonds, that are the blue and green bonds that are facing the horizon? Some of them are facing up, and some of them are facing down. When your axial bond goes down, your equatorial faces up. When your axial bond goes up, your equatorial faces down. Okay? So that's something to remember. So here, this is going, axial is pointing up, so your equatorial has to come down. Remember, it's about 109 degrees. So this is your 90, so it has to be below that. And if you want to know exactly where, try to draw it parallel to the alternate carbon here. So here's a carbon that's going down, so you draw it parallel to that. That's your equatorial. This is your valley coming down, so your equatorial has to go up, so you can draw it parallel to the carbon here. Same here, alternate bond, parallel to that. Those are your equatorial bonds. Over here too, your equatorial is going up, and you can draw it parallel to this one. Okay, and this can be parallel to this, and this can be parallel to this. So if you draw those bonds parallel and alternate them down, up, down, up, down, up, you're going to get the perfect chair. Let's do this one. Is just going to go a flip, flip. All right, and look what happens to the yellow and the gray bonds, the axial bonds, when you flip them. They're all on the sides. They became equatorial. I'll do that one more time. So look at the equatorial bonds. Look at the green and the blue bonds, the equatorial bonds. See what happens when I flip them. they all become axial. Okay, I didn't break a single bond. So therefore, whatever was above the ring is above the ring. Whatever was below the ring is below the ring. That's really important when you're trying to fix cis and trans. So this is not a resonance or anything. It's just an equilibrium. And so here, all of your vertical bonds are now going to go up here, here, and here. So if I number this 1, 2, 3, 4, 5, 6, the 2, 3 is actually the bond that's coming towards you. So if, let's say this is 1, 2 is coming towards you, 3, 4 up, 5, 6 away from you. So this is actually a 3D structure. It's not a flat structure. You could think that this is kind of like a wedge and this is kind of like a dash, but we don't draw wedges and dashes. All right, so here on 1 now, your equatorial becomes axial. On 2, over here, this is going to be your 2, and your 3 again, the same thing's going to happen. Equatorial becomes axial. Okay, and 4, 5, wherever you have a mountain, you have a tall tree. Wherever you have a valley, you have a tube well going down. So number 2, this is going to go down, vertically down. 4, same thing. It's going to go vertically down. And then you can have a 6. Your down bond is down. Those are your axials here now, okay? So this over here is your axial. Over here, your equatorial bonds. Equatorial bonds became axial, and now that means your axial becomes equatorial, all right? So over here, your axial bond is going down. When you move it up, it's going to go up, all right? You draw parallel lines to draw a line here parallel to that. You draw a line here parallel to this, and you draw a line here parallel to that, okay? And over here, you can draw a line parallel to that, and over here, you can draw a line parallel to that. So you can see that all of your equatorials became axial, and your axials became equatorial bonds. And this only happens, in chairs, all right? So now that we know how to draw our axial equatorial, let's put some stuff on here and then see, how stable they are. So here, the chair is about 0 kcals per mole. Potential energy, this is the potential energy increase due to the non-bonding interaction. Now, this doesn't mean cyclohexane has 0 potential energy, because if you burn it up, you'll see it's a fuel, all right? So it's got a lot of energy in those bonds, but the non-bonded interactions that we're talking about in conformational analysis, those don't exist, okay? Just because there's no torsion, there's no angle strain, and there's no steric. All right. No wonder we're eating it all of the time, and we love it. All our donuts, and they all taste so good because they're all so stable. All right. Let's see how this cyclohexane goes from this chair to the flip chair. Does it flip like that? Apparently not. It goes through a half chair, then it goes through a twist boat like a pretzel, then it goes to a boat. Well, then it lets down the other side, goes to the other half chair, and then again a twist, and then it goes all the way to the second chair form. All right. So if you were to draw this out, you would start with, let's say you start with a chair, that's 0 kcals. This is potential energy due to the non-bonded interactions. When we say non-bonded interactions, what we are saying is there's no torsion, the amount of torsion, angle strain, and steric, all right? So all of that would constitute what we would call a ring strain, all of them put together. So that if you start with one of the chairs, it's going to go to a half chair, which is about 10, so all the way up here. Then it goes to a twist boat, about a 5.5. Then it goes to a boat, about a 7, then it goes back again to a twist boat, then it goes to the next half chair, and it goes to the other chair. Okay, so let me label this. Start with A, then you go to B, then you go to C, and here's your boat D, and again you go back to your C, and then you go back to the other B. I'll put B prime, and then you would go to your E. All right, so that goes on probably millions of times per second, just a cyclohexane at room temperature. It's really super fast. All right, but when you put stuff on it, things are a little bit different. Let's say we have this cyclohexane here, and well, what's the point in just having a plain old ring? Let's put a substituent on here. I'm just putting it over here. The question is, do you want to put it here, or in the equatorial position, or the axial position? What do you think? Where do you think it's going to have less disturbances from its neighbors and, you know, all the people around it? Where is it going to be free to go move around? Well, over here, let's look at this. If you look at this, and you might think, oh, it's a lot free to move around, but look at what happens with these hydrogens here. They are kind of close by, too close for comfort. Okay, so there's a steric interaction here. Even though hydrogens are small, it's still like an electron cloud here. So therefore, you're going to have 1, 2, 3 carbons away between 2 axial bonds. So that's called 1,3 diaxial. You have 1 here, and then 1, 2, 3 carbons away, you have another one. So that's another 1,3 diaxial. So every axial group will have 2 1,3 diaxial interactions. That means the steric on the group 1, 2, 3 carbons away, that's axial. All right. So you have 1,3 diaxial. What else do you have? Well, if you look at this and think of this, just this part, okay, just this part as a butane. Well, if this is your butane, just this part, just the right hand side part, then you know this carbon, this CH2 here and this CH3 here are gauche. So you have a gauche interaction with this. So if you can have one on this side, obviously you can have one on the other side because this is symmetric. So here's another one, and here if you look at it like this on the other side, you can see this is a 60-degree angle between this CH3 and this CH2. Okay, in a butane you had CH3 60-degree angle. Here you have a CH3 CH2 at a 60 degree. So you have 2 gauche interactions, and we know that in a cyclobutane that was 3.8 per butane gauche interaction. So all of these interactions increase the energy of this molecule. All right, so substituted cyclohexane, let's take the simplest possible, which is going to be just a methyl cyclohexane. And so there's again 2 ways of drawing chair forms, and we will draw both chair forms, and then we will decide which ones, you know, are more stable, and we can also do a calculation. Now we have values here, A values. What does that mean? They've calculated the difference in energy between a group, just one group at a time, when it's in the axial position versus the equatorial position. That difference is called the A value. So if you have a methyl group, the axial group has 7.3 kilojoules per mole more than the equatorial, because the cyclohexane would be the same for both. It's just this group that causes the extra strain, okay, by bumping into this and having a 1,3 gauche interaction. So let's draw this out. So here again we're going to do the same thing, 2 parallel lines, and then you're going to put your other line, open it up like this, same angle. Then we can connect this like this, all right? And if this is 1, well, you can put your cyclohexane like this on the side. It's the equatorial. Your methyl group, H, H. And this is going to be hydrogen. This would be parallel to this, okay, the alternate bond. Now we can then flip it up, okay, and you know equatorial from these values is going to be in this direction. So here, now we're going to draw these down and then open it up and reflect on this side and on this side, and then you can connect them. Okay, and this is again 1, 2, and so on. So on carbon 1, this pointing up is vertically up, and that is going to be your H, 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 and this is going to be your equatorial. All right. So you can see that this is going to have 1,3 diaxial interaction. Okay. And since it's a steric, we can put it, indicate it like that. 1,3 diaxial steric. Okay. Over here, these hydrogens are pointing up. There's over here 1,3, but this is pointing away. All right. So there's absolutely no 1,3 diaxial here. Okay. It's because it's away. And the other thing is the gauche interaction between this and this. That's a little harder to see, but if you can draw a Newman projection like this, it'll be easier to see. So you're going to look through this carbon and this carbon, this carbon and this carbon, okay, the two sides. So here, this is your axial. Let's draw this out first. It's just like this. So here is your front carbon. So you're pretty much looking at it like this and like this. So your front carbon is going to be number 1. And you're going to go up CH, H, H. This is the red, this group here. Then you have a hydrogen going to the side of that. And the hydrogen's pointing down like that because you have a open 109.5. Then you have this lip going down. Can you see that? So that is going to be going down. Now you're going to look through this and draw a Newman projection through here. These are all hydrogens. This is your front dot with 2 hydrogens. This is your back circle with 2 hydrogens. Okay, so here this is going to go all the way over here. So you have 2 Newman projections, because you can think of this as kind of 2 butanes. One is this butane and the other one is this butane. All right. So these are all hydrogens, so we're just going to put this like that. Then the back carbon, again, they're going to be staggered. And so this is going to connect with this. And here, the back carbon also would have hydrogens like that. Okay, so just like this. So these are the hydrogens at the back. And these are the hydrogens at the back here on this side. All right, so this is basically what you're drawing like that. All right, so now these are CH2s. You can just draw CH2 because we are not really looking through here. This is number 1 carbon. So here, this is a little bit more obvious because, you know, in your butane gauche interaction that you drew, you had a CH3, CH3 bumping heads, and that's what is happening here. This is your gauche interaction. And you can have one there, right? And that's, if you look through here, you can see how you would have one here as well. So I'm going to indicate those in blue. And this would have another one here. Okay, so you have 2 butane gauche, and what else do you have? Well, these hydrogens are going to be bumping into each other as well. 1,3 diaxial and gauche. And gauche interaction. Okay, so here are 2 gauche interactions. So all of this is raising the energy of the axial over the equatorial by 7.3 for this methyl group. So here's your axial. And here's your equatorial. Just for practice, if you want to draw equatorial in the Newman projection for the chair. So here is your, this is going to be in your equatorial position. This is coming to a side. So if you look at it, your methyl is coming to a side, hydrogen and this carbon. And here, so these are the up and down carbons like this. And here now you're taking this and pulling this up. So this is going to come down. All right. So you can see this lip is going up, then the back one is going down. And here, this is your other Newman. Okay. Hydrogens on the side, hydrogens on the back. So no torsion, which is why the chair is the best. So let's draw it out again. So here, if you draw this out, you're going to have, again, looking through here and here. We can draw that out like that, looking through here and here. So I'm just drawing an eye. If you're wondering what I'm drawing, it's just your eye looking through here. So on the front carbon here, your methyl is coming to a side. Then you will have this hydrogen go down. And this is going to be this CH2. Now it's flipped. So this is up and this is down. Now on this carbon, this hydrogen, so you have hydrogens here. Those are these two hydrogens. This is going to be your circle looking through there. And there too, you have a hydrogen here and a hydrogen here. This is coming down, which is going to go, so this is your front carbon number 1 circle. So this is going to go down, CH2. Now on this carbon, so this is your carbon going down, this is your CH2 going down, this is what we have drawn as CH2 here. And now you're going to have a hydrogen and a hydrogen behind this, going up vertically and going to the side, okay? So those are just, just to show you that you have the same molecule flipped here, exact same molecule, all right? Now, over here, do we have any gauche interaction with this carbon here? Nothing, because these are all pointing away, all right? So these are like almost like anti, which is the best, right? Do we have any 1,3 diaxial here? No, this is not even axial, so why even speak of 1,3 diaxial? So there's no 1,3 diaxial here. So that's the main reason why this is almost like a cyclohexane. This is about a 0, and this is 7.3 kilojoules per mole higher in energy than this. All right, what does this mean in terms of distribution? Like, do you see this molecule all of the time or some of the time? How much of a distribution do you have between this? That means, what is the percentage of axial, or what is the axial equatorial ratio? That's what we're trying to see. Okay, so we can calculate that. So we know the total strain energy, or the ring strain here, is 7.3. And we know from Gen Chem that delta G is minus RT ln K under standard conditions. K equilibrium, and that's pretty much what we're trying to find here, the K equilibrium. So if you take K equilibrium, then that is going to be e to the negative delta G over RT. So we can go in and put numbers for this and try to calculate what that is going to be. So here, this is going to be e to the negative 7.3 here, divided by, this is, so it has to be 10 to the 3. This is actually in kilojoules per mole, and our value is 8.314 that we learned from joules per moles per Kelvin that we learned from Gen Chem, the same value. So because that's in joules, we have to convert this to joules, so we multiply by 1,000. divided by 8.314 joules per mole Kelvin times 298.15 is the room temperature, 273.15 plus 25 degrees. And so that's Kelvin. And so here you are going to get over here a ratio 0.05253. Okay, that's your K equilibrium. So we know that K equilibrium is going to be, the way we have said it, is products over reactants. So K equilibrium is going to be the axial amount over the equatorial amount. And that is going to be 0.05253. Okay, so the axial here is going to be 0.05253 times the equatorial amount. And if you want to do the percentage of axial, the percentage of axial is going to be the amount of axial over the total, which is axial plus equatorial, times 100. Okay, so we can substitute this for equatorial. And equatorial is axial over 0.05253. So substituting these over here, percentage axial is going to be 0.5253 equatorial, and you're going to have 0.05253 equatorial divided by 0.05253. Okay, so you're substituting this for axial here. So if you take the equatorial out of here, so that's going to be 0.05253 equatorial. And if you take the equatorial out, it's going to be 0.05253 plus 1. So that is times 100 because it's a percentage. So that's going to be 0.05253 divided by 1.05253 times 100 is 5%. So the percentage of axial is only 5%, right? And you know that means almost entirely everything is on the equatorial side, 95%. This is at room temperature. So therefore, whenever you have a possibility for a molecule in a cyclohexane conformation to have a substituent on the axial position versus a substituent on the equatorial position, it's always going to choose the equatorial position. Less steric and less gauge interaction, which is also steric. All right. Okay, I will see you soon. Talk to you later, and we will come up with more substituted cyclohexanes for you. 1, 2, 1, 3, 1, 4, 1, 1. Stay tuned, guys. Bye.